In this paper, we propose a new method to compute compatible triangulations of two polygons, which allows us to create smooth transformations between two different shapes. We call a vertex pair of a polygon valid if vertex UI is visible from uj and at least one of the two vertices is a concave vertex. We compute the valid vertex pairs for both the source and target polygons. We collect all the common valid vertex pairs of the source and target polygons, among which we select the one that can maximize the minimum interior angle. Now we triangulate each sub-polygon of the source polygon using Delaunay triangulation. In the second stage, we map the triangulations back to the corresponding polygon using linear transformation. In the third stage, we refine the initial compatible mesh created in the previous phase such that we can increase the proportion of regular triangles and make the mesh more uniform. Here, we show examples of applying our method to compute compatible triangulations. Our method introduces a very small number of Steiner points while the quality has been improved significantly. This benefits smooth transitions of shape morphing. Here is one example of comparing different compatible triangulation methods. We can see that Surazhsky-Gotsman's method generates some long thin triangles that may cause inconsistent rotation problem for rigid shape interpolation method. The mesh quality of Baxter et al. Has been improved compared with previous methods, but the long thin triangles still need to be improved. Compared with previous methods, Liuyang et al. Has greatly improved the mesh quality, however, they may introduce a little more Steiner points. Our method generates tessellations similar to Baxter et al., but with a significantly simpler algorithm and improvements in mesh quality. We can see that our method generates less number of Steiner points than the other methods, however, we achieve better mesh quality compared with the others. Our inputs are the source polygon with texture and the target polygon without texture. We then compute the compatible triangulations to build a bijection between the two polygons. With the compatible mesh, we map the texture of the source shape onto the target shape. This is the mapping result of using Liuyang et al.'s method. We can see some artifacts around the back of the alligator. This is the mapping result of using Baxter et al.'s method. We can observe some undesired distortion for both the tail and the back of the alligator. This is the mapping result of using Surazhsky and Gotsman's method. We can see some serious distortion around the abdomen of the alligator. Here, we apply the rigid shape morphing method to generate the transformations with texture. Our method can be used by the industry to generate character animation. The artist can simplify their work by only drawing keyframes, and our system can be applied to automatically morph the keyframes. To demonstrate the effectiveness of our approach, we test the proposed interactive animation creation system using human silhouette as our source shape input. Due to the lack of topology information, building compatible triangulation for shape with self-occlusion cannot distinguish the overlapping parts. In order to enhance the compatible triangulation with self-occlusion, we introduced the calibration shape. The calibration shape helps to extract the topology information such as the deformation control points, and it also gives us the full body texture of the source object. We then build a compatible triangulation between the calibration shape and target shape. Lastly, we deform the mesh of calibration shape into the mesh of source shape with occlusion using the control points. We use Kinect as the input device of our interactive animation creation system. Because it simplifies the work of capturing the silhouette and texture of the source object. The system captures an image of the user, and then the shape of the user is gradually transformed into the target shape. After enhancement, we can identify the overlapping parts and generate sensible transformations. We can see that the limbs of the source object are transformed into the wings of the airplane. We detect overlapping regions and adjust depth on the fly.